Here we go, kinematics equations. What we're going to start with the kinematic equations because one we've done constant velocity. It was an easy equation. Acceleration equals velocity over time. I'm sorry, constant velocity was change in position over change in time. Acceleration was velocity over time. I gave you some basic worksheets and I told you to listen, list the givens. I know you're only using one equation. It can be simple to do, but I was telling you to go through a process of list the givens, plug in, solve, all right? But now we're using kinematic equations. We're going to expand the equation base here. They're all still based on acceleration and velocity, so, but they're just a little bit more dynamic as far as how they are used, all right? And eventually where we're going to go with this is things such as projectile motion, all right? If I was to toss this to you, ready, catch? So catch it, all right, and then toss it back to me. And it's one of those, well, how do I know to make this projectile go to him, all right? I have to give it an initial angle. Why? If I went straight to him, what's going to eat away at it? Gravity will go straight. So I have to compensate by going up a little bit, right? I can't toss to him and do this. Didn't quite get there. I knew in my head that I had to make sure I applied a force, applied an initial velocity to go this at a height, the counter gravity, so that when it does go to him, it gets to him, all right? And then when he tosses it back, same thing. If I wanted to go, let's see, wake up so I can, well, here, stand up for a second. Stand up. You're asleep, I can kind of wake you up. Stand up for a second.
Get up, Troy.
Put your hands up like this. Because when I want to go to Nathan, I gotta now do this. I can't do it like this, I whack him in the face, don't I? So what I have to do is I have to adjust for a higher trajectory, right? So I have to adjust for a higher trajectory so it gets over to him. So I have to change my launch angle, which means it'll have a horizontal component, vertical component, which will get down. So if I do that, it gets to him. If he wants to get it back to me, he's got to do the same thing. So that's projectile motion. All right, thank you very much. You know, we also look at things as free fall. All right, we start and we drop something from rest, or we drop it from the edge of a cliff or from the edge of a building, and it does this. All right, and it's going to be accelerating down because of gravity. And so we're going to start calculating those kind of things in there as well. We're going to start with the root equations. All right. So, so here's how the definition of this, the set of equations utilized to determine unknown information about an object's motion. If other details are known, the equations can be used for any motion described as being either constant velocity motion, which is constant velocity, there's no acceleration, or constant acceleration motion, with which there is acceleration. Each of the kinematic equation includes 4 variables if the value of the 3 variables are known. Then the value of the 4th variable can be calculated, all right? Now, here are the equations you're going to use. 1, the 2 you already have really are concepts, not equation. Velocity equals displacement over time, and then acceleration is velocity over time, all right? Now you have the addition of 4 new equations to solve for things like velocity, initial or final, acceleration, time, and position, all right? And I'm going to rewrite these kind of in terms without the deltas in them because they actually solve for the change in whatever, but in all purposes, you're just going to solve for whatever the variable is. The first one is displacement equals initial velocity times time plus 1/2 a acceleration times time squared. So you know sometimes I kind of took the deltas out of it. It's really the same thing. All right, the second one is displacement is going to equal 1/2 of initial velocity plus final velocity times time. That's going to be the second one. The third one is final velocity equals initial velocity plus acceleration times time. All right, and then of course the last one is final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. You'll use one set of these equations depending on what? We'll get to that in a second, all right? And when we get into 2D motion, what goes along the X and what goes along the Y, these will be applicable to the X axis and the Y axis, in this case, horizontal or vertical. What is happening in the horizontal, what is happening in the vertical? Because when I toss this over to him, nice catch. All right, toss that back from there, okay? There you go. When we toss it, it's anything at an angle is broken down into an X and a Y, right? So anything launched at an angle has an x component and a y component. So we can apply these to the x and y's. We won't do that yet, but that's what happens with anything that's a projectile. Got it? All right? So any questions on these equations? All right? So the kinematic symbols, I'm not going to go over these because we already know these. We know what displacement is, we know initial velocity, final velocity, acceleration. We already know the variables. If you need to reference them, there they are again. The common phrases, I call these buried givens. These are variables that are given to you, but that are not stated in numerical form. One of them is starts from rest, initially at rest, means that the initial velocity is 0. It doesn't have to state initial velocity is 0. If something starts from rest, you can apply that variable, to that value to that variable. Conversely, when something comes to a stop, comes to a rest, the final velocity is 0 meters per second. All right, is everybody with me here so far? Pretty straightforward. Buried givens. Something speeds up, slows down, turning a corner, travels in a circle, changes direction. That means you have an acceleration that's some non-zero value. There's acceleration going on. All right. Speeds up, slow downs are going to be the ones that you will usually see in what we're doing here. And then, of course, if something is going constant velocity, there is no acceleration. We talked about that. All right. Another one I want you to sort of write down that we're going to get to, that you're going to kind of chase this almost all throughout the year. Acceleration to gravity equals negative 9.8 meters per second squared. That is a buried given. When we talk about free fall, when I drop something from rest and it free falls, a buried given is the acceleration of gravity is happening, isn't it? So you can assign that as a given in an equation if that's what's happening. All right? Any questions on buried givens? All right, any questions? Good. So here's how this works. Here's sample problem 1. I'm gonna go over a couple of samples, all right? And everything mathematics, and everything mathematical and science, most science has a procedure to solve. If you think about it, any mathematical concept or scientific concept is gonna have a procedure to solve. Follow the procedure, you'll get to an answer as long as you do the math correctly. Okay, so here is the procedure on how to solve kinematic equations. And you're going to need to follow these procedures to make sure you choose the right equation and then solve accordingly. Sample problem 1, and it's in your notes. A car is traveling at 30 meters per second when it passes marker A. It's accelerating at a rate of 3 meters per second squared. 2 seconds after passing marker A, it passes marker B. How far apart are the two markers? All right. Does that thing show it's recording? Yes. Okay, that's what I thought. I thought about it for a second. Anyway, the first thing you do is you list your givens. When you list your givens, okay, it's going to help you find the equation to use. So the best thing to do is list what you're solving for. What are we solving for here? What variable? Yes. How far apart are the two markers, which means displacement equals question mark. That's the thing we're solving for. All right. Now, what are my other givens? What is 30 meters per second?
Your initial.
That's my initial. And how we know is we got to read when it passes marker A. This is being measured from marker A to marker B. It starts at marker A and finishes at marker B, which means marker A is my initial component. So I'm going to put initial velocity equals 30 meters per second. And does signage matter here? Yes, and you're going to have to watch it. Sometimes it's implied here. There's an implied positive here, but you got to still read into the details. Is this thing moving away from its designated origin? What's the origin in this? Marker A, right. Marker A is the origin. That thing's moving away from marker A, so we know that that thing is going to be positive, right? And if it's accelerating at a rate positive 3 meters per second, okay, which pretty much means this thing's going to speed up. So acceleration equals 3 meters per second squared. Cool. What's another variable here?
The time is 2 seconds.
Yeah, 2 seconds after passing marker A. 2 seconds after A, it reaches marker B. That's our time, isn't it? So time equals 2 seconds. So now, have we got all of our variables? We pretty much do, don't we? Here's the key. The success in this is going to be using your variables to figure out which equation to use. I need an equation that has displacement, initial velocity, acceleration, and time in it. So you go through your equation bank and realize which one has all 4 of those that I can solve, okay? And then if you look at them, you're going to realize I have this one, displacement, change that. You're going to look at and realize the one that has it. So I'm gonna put displacement in pink, so that's what success we're solving for, equals initial velocity times time plus 1/2 acceleration times time squared. Because I checked my equation and said, yep, that equation has that one, which is what I need. That one has the initial velocity, that one has time, that one has acceleration, of course there's time again. Bingo, that's the one we use. Because you're gonna try to use an equation that has all of them except for one. You get all of them except for one, you can solve. Now, eventually down the road, and you'll see this, is what if you look for all your equations and you see that you have all of them, but the best case you can get is 2 of them are missing. What do you do then? Let's say I was looking to solve for displacement, but I didn't have my initial velocity. What would you then have to do? Take your givens and go solve for initial velocity. It becomes a sub-problem. You then have to, okay, in order for this to work, I have to get initial velocity. Now I've got to go find initial velocity. Find an equation that has initial velocity with your givens, solve for that, then you come right back into the original problems. Everybody see that? And that will happen, all right? But in this case, we found them all except for this. After you list your givens and after you list your equation, what do you then do? Yeah, substitute / plug it in. Okay, so we're gonna plug in these variables. So we're gonna do x equals, my initial velocity is 30, my time is 2, plus 1/2, my acceleration is 3, and then 2 squared. This is straight up solving because my variables by itself, I don't have to do any algebra on this, do I? I now have to run PEMDAS. So what do? Let's knock out that needs to be solved, this part needs to be solved. 30 times 2 is 60, so I'm gonna do 60 plus, I'm gonna do 1/2, I'm gonna do this in pieces, 3, and then 2 squared is 4. Got that piece solved, I gotta do the other side of the sum here. I'm gonna do 1/2 times 3 times 4, 3 times 4 is 12, I'm down to 60 plus 1/2 of 12. What's 1/2 of 12? Is 6. 60 plus 6. What's 60 plus 6? 66. My displacement is 66 meters. There's my answer. Okay? Does everybody see this?
Yes.
All right? Revisiting. List givens. Look at your givens and see which equation it applies. Find the equation that you use. Write it down. Plug in or substitute. Use whatever math. Now this is no longer physics. This becomes a math problem, doesn't it? Then use whatever math to solve. Either straight up PEMDAS, or as you're going to see in a second, algebra to solve. All right, you with me? Okay. Any questions so far? Cool. Notice how I did the procedure. And you need to show work when I give you these kind of problems. Make sure you show work. Sample problem 2, and it shows the givens, by the way. It shows you the procedure on how I did this in your notes. Sample problem 2. A spacecraft is traveling at 155 meters per second when the retro rockets are fired. This causes it to accelerate at negative 31 meters per second. Part A, how long will it take to stop the spacecraft? Is this thing speeding up, slowing down, or going constant velocity? Slowing down. That's what retro rockets do. That's why this is positive 155 and this is negative. Those signs had better be opposite. And I'll state this, if you don't get the signage right in some of these kind of problems, it'll depend on the problems, it could mess everything up. You have to understand what the signage is doing. That's most important. Cool, so I'm gonna list my givens. What is this asking to solve here?
How long?
Time, isn't it? Yeah, time equals question mark. That's what we're being asked to solve. Then I'm gonna list my givens. I have a spacecraft traveling at 155 meters per second when the retro rockets are firing. So now that's my initial velocity, because that's what it was before the retro rockets fired. My initial velocity is 155 meters per second. My acceleration is negative 31 meters per second squared. Cool, how long it will take to, that looks like that's all my givens, isn't it? Is that it? Or is there something else?
We have a final velocity.
What is my final velocity?
0.
Good, yeah. Why? Take to stop the spacecraft. That's a buried given right there that I talked about. So yes, we have a final velocity equal to 0 meters per second. Which equation has time, initial velocity, acceleration, and final velocity? We go to this, we do final velocity equals initial velocity plus acceleration times time, and there it is in pink because that's what we're solving. There's the equation we're going to use. I believe in your notes it rearranges algebraically the equation for time and then it solves them. You can do that if you want. This is a way better way to do it to make sure you don't have to memorize so many equations or do so much rearranging all the time. Plug it in and then do the algebra. So now we're going to plug this in. Final velocity is 0 equals initial velocity of 155 plus the acceleration is negative 31 times t is what we're solving here. Now the variable is not by itself, so we have to do some algebra here, don't we? What's my first move here? Deal with the 155 or the negative 31? 155, isn't it? The negative 31 is being multiplied into this. Remember PEMDAS's backwards cousin, SADMAP. It tells you how to solve 1 and 2 step algebra equations. You have to deal with any subtraction and addition first, don't you? And this is being added on to this, so you can't touch the negative 31 first. What's the opposite of addition? Yeah, we're going to subtract 155 from both sides. Cancel, cancel. So negative 155 equals negative 31 times time. Cool. Is there any addition, subtraction left over here? There's not. This is negative 31 times t. What do we do to get rid of the negative 31? Yep, divide by negative 31. Cancel, cancel. And that's where you get time equals 5 seconds. Cool. Does everybody see what I did there? All right. Now, this has a part B where the time you got for this, now does that become a given for the second part of this? Well, I believe the second part says B, how far will it travel during this time? Now, this becomes a variable, doesn't it? And now what are you asking to solve? For part B?
Distance.
Distance, isn't it? Okay? And now what I'll do is, I won't go over that part of it because you can see how it will go. And then C, find the velocity of rocket 8 seconds after the retro rockets are fired. Here's what I did in the first one, which is a no-brainer. Then this one, here is part B. Now the 5 seconds becomes, from part A, it becomes a given, doesn't it? So there's the givens. And then you ask yourself, which equation has displacement, acceleration, initial velocity? You're going to use the displacement equals VIT plus 1/2 AT squared. As you can see, what this will do is it will plug it in. All right. Plugs it in, it reduces, solves to 387.5 equals 3/8 sig figs. We're not doing anything related to significant figures. Not really used anymore in the scientific realm. All right, what we will do is by default, you will solve to 2 decimal spots, got it? Everything you do in here, you'll solve to 2 decimal spots unless I clarify differently, all right? This is part C, the retro rockets. After 5 seconds, the retro rockets are still firing. Now that rocket's gonna go the other direction, isn't it? All right, and it will calculate out that way if you run it, and notice that it's now the final velocity is negative 93 meters per second, all right? Don't worry about sample 3. You can go over that if you want to. 4. I'll do one more. An airplane taxis to a runway and maintains a constant velocity of 2.1 meters per second. It then moves down the runway and accelerates down to 3.2 meters per second squared for 58.4 seconds. It finally lifts off the ground, determine the distance traveled. It then has the same givens, the VIT plus 1/2 AT squared. This one calculates out straightforward. I won't go over that. All right. Any questions?
Yeah,
Here's what you're going to do. Right now, you're going to do sample problem 5. Coach Lambert's NASCAR race car is capable of accelerating at a rate of 15.1 kilometers per hour squared. How long does it take for his car to go from a speed of 187.4 kilometers per hour to a speed of 243.8 kilometers per hour? Go. Solve for this. I will see what you get, and then I will do it. Everybody. When you get an answer, raise your hand. Yep, how many of you need a calculator? I got some up here.
Yes, sir.
Yep. Yep. Has everybody listed the givens? Has everybody listed the givens? I'll list them too. Does that look right? Yeah.
No, I just had the answer.
Oh, you got the answer? You got it, good. Yeah, that's it. If you get the answer, move on to number 6, sample number 6. That's correct, good. Anybody else get it? You got it, very good. You got it, good, very good. Do believe the one that we use, final velocity is initial velocity plus acceleration times time. When I plug this in, you should get 243.8 equals 187.4 plus 15.1 times time. If you notice one thing I do on this, and I still do this to this day, because if you want to know something that burned Coach Lambert before in his collegiate environment, is running through equations too fast, or skirting, or shortcutting. I always look and make sure I'm putting things into the right variable and or using the right equation. I heard somebody use the wrong, look, that's okay, all right? You probably try to use the wrong equation, realize I'm not getting anywhere. That's okay. That tells you to go back to the drawing board and go right back at it again, that's fine. All right, I look at it, check it, yep, make sure I got it. Now I got to make sure I do my math correctly, which I'm going to subtract 187.4 from both sides. 187.4, cancel, cancel. 243.8 minus 187.4. 243.8. 243.8. And as I just did, make sure you punch things in the calculator correctly. 56.4. 56.4 equals 15.1 times time. We're going to divide both sides by 15.1. Cancel, cancel. Time equals 3.74 seconds. Is that right? Okay. Always try to box in your answers. All right. Let me see what we did there. Da, 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 da. Run the procedure. As simple or easy something gets, run through the procedure. All right. Double check your answers. Double check your math, especially if you have time at the end of a test. I tell you, once I got late in my collegiate career, I was one of the last people to finish tests. Why? I want to make sure I did the work correct. All right. I used every amount of time. I never turned anything early. Why? Took my lumps early, realized, oh, if I just would have done this, simple math errors. And then you're at the mercy of a professor who might not give you partial credit. All right, you either get it or you don't.
Why do you use that equation to find the time of it?
What's that now?
Why do you use that certain equation to find the time of it?
It's given the variables that you have.
Okay.
Yeah. Did you try to use the other one?
Yeah.
Which one did you try to use? It's a good question.
Well, I almost did all 5.
Did you try to use this one? Did you try to use that one?
That's
Right.
the first one I did.
Okay, cool. Okay, this is an honors class, so you get this. Well, first of all, you're looking for how long? So you don't have displacement for this, do you?
No.
So you can't use it, can you? All right.
That's what I realized.
Yep. Now, you could use it if you found displacement. You have to go off the board. Now, then you could look at the other ones. Then you should say, okay, I don't have this, and I'm still looking for this, probably not the right route to go. Go back to the drawing board, look at this. Do I have anything with VF, VI, A, and T? There it is right there. And then you drop right in, all right? Oh, and I may throw you this, where I have to solve for T, and T and T squared aren't like variables, are they? And we'll cross that bridge when we get to it. In other words, it kind of becomes quadratic, right? Or factoring kind of comes into play. All right. Any questions? All right. Did you do number 6? What'd you get for 6?
8.11.
Yeah, 8.11, isn't it? 8.11 is what you get for 6. All right. Any questions? That's it for kinematics. Sample questions 7 and 8 you'll do when you start getting here tomorrow. Bell's about to ring in about 3-4 minutes. If you want to do 7 and 8, you can, but you're going to do those as warm-up when you walk in tomorrow. Any questions? Sweet. All right.